Good afternoon, everyone. Can you hear me? Students, am I audible? Okay, fine. Okay. So, yes, very good evening, everyone. We'll just wait for a few more minutes and we'll start at 3:30. You must be wondering where sir went. Um, these classes, this P block and all, I'll be taking. Sir is on leave. Towards the end, I'll also share my number so that in case you have a doubt, from the portions which I have taught, you can also like connect with me. Fine. So, how is your preparation going on? Very hectic and full fledged, right? 7th May, the target. So, just around 2 months, not even that. Correct. I know you, all of you are just definitely ensuring that you're giving your best. We are waiting. We cannot start before 3:30. Once it's time, we'll definitely start our discussion. Where you'll be knowing most of the things and you'll be telling me and I'll be listening. P block. Other things are done, right? It's you have P block and D, F, metallurgy, right?
Coordination compounds also.
Thank you, thank you, thank you for reminding. Yes, he told me. I just missed it out. Yes, thank you. PDF, metallurgy, coordination. Fine. We'll start right at 3:30 because it's you know how P block is huge. At least one block per class. Also, if we try to do without compromising on the content, then it would be fine. Anyways, a minute more in this system's time clock. I mean, very good afternoon. Yes, sir. So it's 3:30 by my system's time. It's a huge portion to cover. Good evening, good afternoon. Anyways, good afternoon, everyone.
Good afternoon.
A very good afternoon. As you can see, my name flashing, but still, I'll just introduce myself, Sushmita, Sushmita Bandyopadhyay, and I'll be taking your P block. I'll share my number also and whenever you go through and you have doubt anything based on the portions like I've taught, you can always feel free to get in touch with me. Fine. So here we start. So I hope everyone knows that the boron family contains boron, aluminium, gallium, indium, thallium. And what's the last element? We don't bother much about it, right? The radioactive one?
Nihobinium.
Nihobinium. My God, perfect. Yes, correct. So boron, you are a non-metal, followed by remaining all metals. But yes, the last one being radioactive, will hardly read anything about it. Just comes in the slides and then says bye bye to us. So it's nihonium. Nihonium. Okay. Anyways, everyone knows, no, after atomic number 100, we can basically use the IUPAC nomenclature also. So once you know the atomic number, and you can do that by adding 32 to the atomic number of thallium, and you get its atomic number, and you can go for its IUPAC name also. Anyways, that's not very important. So boron is a non-metal, and the remaining all are metal. So these are all the elements of the boron family. Students, the melting point of a substance, what is the basis of deciding that? Yeah, there are a lot of exceptions in chemistry, I do definitely understand. But say for example, if want to say that something has a high melting point, right? Now melting point, something has a high melting point while other doesn't. So what does it depend on? Its lattice structure. If the lattice structure is quite compact, fine. Okay, if it's metal, then it should be strong metallic bonding, agreed. If it's a non-metal, the bonding between the other, say for example boron, the boron atoms which are held together, just see the way they are bonded here, it's extremely compact. So if it's extremely compact, you have to take more pains to break the bonding. The bonding is strong, you take more pains to break the bonding. And if the bonding was weak, like they were having cold war between themselves, so it's easier to break the bond. In other words, the crystal structure is basically one of the important deciding factors to decide the melting point. And hence we see that your boron has extremely high melting point because the compact arrangement of the atoms here indicates. You can see here. Yes. So all the 12 atoms are held together very strong, in a very strong manner, very strong bonding. So it has extremely high melting point. Other people who have joined, very good afternoon. Hi, hello, we'll do later. Let's continue. We are discussing group 13 of p block elements. So boron is a non-metal, hard, inert, poor conductor of electricity. There are no free electrons. That's the reason it's a poor conductor of electricity. Everyone must be already knowing that gallium has extremely low melting point. Do you know the reason why?
Introduction
Anyone?
of d orbital.
Sorry?
Introduction of d orbital. Let's say.
A d orbital has something to do with its small radius, something like lanthanide contraction. I'll explain transition contraction here, as I read in JD Lee reference there. It was given that the gallium, here see 12 atoms are holding each other strongly. Ga exists as Ga2 molecule, so it's just a small dimer and the bond is quite weak. That's the reason it has a very low melting point. Basically, the least melting point. Important. Values, don't remember. Trend, please do that. So, boron, aluminium. Then thallium, indium, gallium. The reason is the way they are arranged. So for boron, we know how the 12 atoms have a compact arrangement. And I know, as I told the reference, I read there about gallium. The two, see, without reference, we don't have any other way out. There must be some, either we need to do that experiment in the lab, we should do that research, or we should read it somewhere. So with respect to that, gallium is bonded to just another gallium atom that also not a very strong bond, so has the lowest melting point. So just the trend, try to remember as much as possible. Boron, aluminium, in thallium, then indium, gallium. The first, best and the worst one, so definitely sometimes in that way you can eliminate the options. Fine. Now, the next thing is density. Students, how do you decide the density order? Or to some extent, this also has to be experimentally known, because density is mass by volume. So if more mass is concentrated in a smaller volume, density will be more. Correct? No? So what do you think? Sometimes it works, some trends, but other times you have to let's see it works or not perfect. It works here. It's showing a constant increase in density. Yes, yes, yes. As we go down the group, well and good, easy to analyze, but in certain cases, exceptions are seen. So be careful when you read. So just be particular about the melting point, highest boron and lowest gallium. When I'm repeating, when I repeat, gets registered better. And here it shows a constant increase as you move down the group. Atomic radii, tell me, it has been asked also previously. You know the anomaly? Tell me. Dash has lower radius than dash. And you know this puzzle. Atomic radii should increase down the group, but there is some anomaly here. And the reason is transition contraction. Yes. Yes, Nandana. Yes, yes, yes. Indium more than thallium? No, no, no. No, 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 no. Not really. Basically, indium and thallium have almost same radii, but when I looked into the NCRT values, indium only slightly less than thallium. The anomaly here, as mentioned by Nandana as well as me, is it's gallium. I'll explain it here, students. It is gallium which has lower radii than that of aluminium. This is the anomaly. No, not inert perfect. I'll explain that. So you have aluminium, neon, 3s2, 3p1. You have gallium, argon, 3d10, 4s2, 4p1. What is special here? The additional d electrons. How many? 10, which will have poor shielding effect, as a result of which effective nuclear charge will be more or less. Tell me. Today, we have to know each other. I have no idea. So, if shielding effect is less, effective nuclear charge is more. It's not doing its job properly of shielding. The outer electrons are easily attracted towards the nuclei, and hence the effective nuclear charge and the nucleus ability to pull the valence electron is high. So poor shielding effect because of the additional 10 d electrons here. D and F. F the least. This D and F are poor shielders. F the worst shielder. So due to poor shielding effect of these 3d electrons, effective nuclear charge is more. So if it's the nucleus is pulling the outermost electron closer to itself, what will happen? The size decreases. So due to poor shielding effect, that effect is more and size is less. Getting my point?
Yes, ma'am.
Yeah, please feel free to ask. I'm not at all scary. I don't scold. Don't worry. I don't scold. So none of us does. Yes means you can feel free to ask me any simple thing. Yes. I hope you got the point and the anomaly. And in that case, you should also ask me, ma'am, thallium has F electrons, and in that sense, the anomalous behavior should be seen here. It's actually experimentally what the values have checked is the values are quite close. It's not that thallium is drastically large. It should have been, no. As you go down the group, the inner electrons increases, the shell increases, and but due to this lanthanide contraction, by the way, I'll use the term here transition contraction, and you'll use the term lanthanide contraction due to which the drastic increase which I should have observed when I moved from indium to thallium, that's what I don't observe. They're basically similar, and this one more or this one less, that actually depends on the experimental order, experimental value, I mean. So here gallium is slightly smaller, slightly, the change is only very slight, slightly smaller than aluminium. Indium is only slightly smaller than thallium, though Could have been the other way around, but that's the value which indicates. And here, instead of a drastic increase, what you see is almost similar sizes due to lanthanide contraction. But the values reveal indium is still slightly smaller than thallium. So the anomalous behaviors, I'll just remove this, is only seen in this aluminium gallium order. Fine. Very important, not important, very important. Important. Fine. Now, when we proceed, ionization enthalpy. Ionization enthalpy should follow exactly the opposite order as that of the radii. Should, I mean, the size is more, ionization energy should be less. So, the order of ionization energy should be exactly reverse the order of atomic size. But again, experimentally it was observed that the ionization energy order is boron the most, no doubt. After that, no. Why I was expecting this thallium to come little up is its nuclear charge. What I mean to say is the number of protons, atomic number is very high, no? So a lot of protons are there. So those protons will attract those electrons, outermost one, very strongly. And hence, this comes up a little more in the order. And gallium to aluminium, I hope you understand. If gallium, if you have a smaller size than aluminium, then your ionization energy should be small size, ionization energy should be more, and indium the least. But again, okay, yes, I'm talking to Faizan. Yes, Faizan, correct. But again, these stories and all we can tell only after you remember the trend. So this again is an important one. Students, if I have to like really not remember all and only a few. First, atomic radii and ionization energy is a must. Density is not troubling you, it's just increasing. So it's, and the next one is melting point. So three things, which is little anomalous. The melting point, atomic radii, and ionization energy. Request you to learn this and go. Okay. Tell me if you have noticed what I wrote on the previous slide, all was already there. Did you remember the trend of ionization energy? Boron, thallium, gallium, aluminium, finally. Okay,
Indium.
good, good, good. Very good, very good, very good. Chalo, tell me this one also.
Group 13.
Absolutely, because they'll not have a complete octet. No, so think of BCl3 or BBr3 or Bi3. Yes, yes, yes. Tell me.
Four, two,
Absolutely.
and 3.
Yes. What we don't have is time, so we are like trying to make it fast. Yes.
Aluminium.
Absolutely. Very quickly.
Aluminium greater than gallium.
Yes, should have been the other way around, but due to transition contraction, absolutely. Good. Students now, yes. Inert pair effect. Inert pair effect is observed in which all group, students? Because I'm starting with 13. Basically, my plan is definitely to cover the entire P block.
13, 14, and 15.
13,
Absolutely.
14.
The last member of 13, 14, and 15 group. They have no a lot of protons in their nucleus. So there's a lot of positive charge for the last member. And in this, if you see the configuration, since I'm talking about the 13th one, say take thallium. Say I have 6s2, 6p1 configuration thallium, right? So what happens is here there are maximum number of protons. Nihonium, leave it. It's a radioactive substance. So there's a largest element in the sense that it has maximum number of protons. If you have lots so many protons, you can attract these electrons effectively, and s is closer than p orbital. S orbitals are more penetrating in nature. So s orbital is closer than p, and s orbitals are having like ability to undergo more penetration of the electron cloud. So they're more closer to the nucleus. And the nucleus contains, you must be telling that, ma'am, this is true for any NS2 and P1 case. True. But there are not so many protons in the nuclei, in their nuclei, so of aluminium or gallium or etc. etc. to attract these electrons or hold these electrons that strongly. So the number of protons in the nucleus being the highest here, I'm forgetting neonium, sorry. So it can attract these s electrons more strongly than this p. Why? S is closer than p and it has greater penetrating power. So thallium says, I don't want to lose my precious 6s2 electrons. So I would be more happy if I can just get rid of this, and I can clearly say that TL plus 1 is more stable than
TL plus three.
TL3 plus. Correct. That's what has been written here. So the stability of the plus 3 oxidation state decreases while the stability of plus 1 oxidation state increases down the group, and that's all due to anywhere it has been mentioned. Inert pair must be there. Effect. So it's thallium in which the plus 1 is more stable. In all other cases, I'll consider plus 3 to be more stable than plus 1. Inert pair effect. Fine. Definitely, I'm telling you something which you'll read and come and definitely let me know tomorrow what and all doubts you have regarding this. Now, bad. I didn't want to click this step. Anyways, is the oxide of boron, which is acidic. Aluminium and gallium oxides are amphoteric. The oxides of indium and thallium are basic. So, because non-metals form acidic oxides, metals usually form basic oxides. But yes, there are certain metals which can react with both acids as well as bases, and hence they form amphoteric oxides. With nitrogen, yes, they will react to form nitrides. Boron nitride is formed under specific conditions, and it has one more name in case anyone knows this. Boron nitride has one or another famous name. You're very close, Faizan. Inorganic benzene is actually borazine or borazole. Inorganic graphite, because it resembles graphite in its structure. So boron nitride, inorganic graphite. Borazine or borazole, inorganic benzene. I'll show you. Okay. No, no, no. It's absolutely okay. You don't forget it. You are very, very close. That's good. Yes. Now, except TiI3, because Ti plus 3 will not be very stable due to its inert pair effects. They will form trihalides with halogens, which is the moment you I see the slide, I remember about certain trihalides. Which one? Which are those? Which are the ones? The moment you think about this, you remember about AlCl3. No problem. Okay, that's correct. Definitely, that's correct. The first thing which came to my mind is like BF3, BCl3, etc., etc., etc. No problem. Good. So these are the ones which this came to my mind, and when Faizan told, this one also came to my mind. I will tell you something special about these things, but let's have a general discussion is going on. Let's continue, and then I'll discuss about those specific things. Yes. So you'll see that aluminium. Okay, fine, fine. Yes, aluminium will react with HCl, aluminium solid, to produce AlCl3 and hydrogen gas. Here, I would like to tell you something. Whereas aluminium and gallium, being amphoteric in nature, can react with alkalis as well. So mainly my focus is aluminium, which can react with HCl, an acid, to form AlCl3 and H2, liberate H2, while Al can also react with NaOH, an alkali, to produce NaAlO2 dot 2H2O because it gets hydrated. Otherwise, NaAlO2 is known as sodium aluminate. It's written meta-aluminate. We'll correct it. NaAlO2 is sodium meta-aluminate. what I would like to tell you here is little more weight. Okay, you are basic oxides. Base will not react with the base. So indium and thallium will not react with the alkalis. Fine. Now, so what I would like to tell you is AlCl3. What is it? Ionic or covalent? Covalent without water. If it doesn't see water, it will remain covalent. Ionic in aqueous phase. So what happens is aluminium will split into Al3 plus and Cl minus. I know 3Cl minus. So just wrote one, space is also less. So what happens is now Al3 plus will be surrounded by the oxygen end of water. And here the hydrogen end will be near Cl minus. So minus delta plus end will be there. Plus the delta minus end will be there and it gets hydrated. But for that water is required. So it behaves in an ionic fashion. It is ionic in nature in aqueous medium. Otherwise it is covalent in nature. And how does it behave? I'll just tell you. Till I complete, just wait for a while. I have to tell you a little more about AlCl3 in the covalent form. Can you recollect it dimerizes? It
Yes,
forms the
ma'am.
dimer. Yes. So I will tell you why dimerizes and why in the case of BF3 it goes for back bonding. Just a minute. Borax. We will follow the sequence and then we'll come back to those points. So I have to tell you that AlCl3, when it doesn't see any water around, no water around, it will prefer to dimerize and form Al2Cl6. Why? Definitely to complete its octet. Why not back bonding? And what is back bonding? I'll tell you. And meanwhile, just know that AlCl3 is ionic in aqueous phase. And without water, in the absence of water, in the absence of aqueous phase or aqueous medium, it shows covalent bonding in it. We'll go for it today itself. Now, borax, a white crystalline solid in which it consists of 2Na plus and B4O5 OH whole 4 2 minus units. Basically, Na2B4O7.NH2O, 8H2O doesn't do anything except supporting work, and remaining two water molecules and the remaining part. They combine and it looks like this. Yes, the four borons. BOB linkages 1, 2, 3, 4, and 5. 1, 2, 3, 4, and 5. OH here 1, 2, 3, 4. This overall is, I mean, B4O5 OH whole 4. B4O5 OH whole 4 is overall 2 minus, and you have 2 Na plus. Okay, and important points, really they are important. I'll put an asterisk mark. By the way, without looking into the next slide where it comes, I would like to ask you one question. The aqueous solution of borax is acidic, basic, alkaline, neutral. Tell me, what is its
Acidic.
nature? Absolutely correct or incorrect?
Like
Absolutely correct or incorrect?
H3BO3 and NaOH both are formed in that case.
Since the both are formed, which is strong, which is weak? The one which is strong, its
Basic
characteristic will be
NaOH. Yeah.
absolutely correct now. Good for answering and now correct answering. Yes, I'll elaborate on that when the slides comes. Yes, good, good. I just wanted to know beforehand. Yes, Arpita also. Very good. Very correct. So before that, please help me find out the hybridization of these borons. This one and this one, same thing. 4 sigma bonds. Can I directly write sp3 and sp2 here? Check. Have a look. There are 5 BOB linkages. 1, 2, 3, 4, 5. Yes, agreed. 1, 2, 3, 4, 5. Agreed. There are 5 BOB linkages. Total BO bonds count, it will be definitely 14. Hybridization. Yes, Faizan, do you agree that two of them are sp3 and remaining two sp2? Yes. Everyone? Others who are wondering, the ones who have joined, I am seeing the change in numbers. So, um, you all can feel free to ask me any doubts in chemistry. And I hope you have understood why I have mentioned that these two are sp2 and these two are sp3. Any doubts?
No, ma'am.
Okay, fine. Then we'll quickly continue. Yes. As was just discussed, hydrolysis means you'll make it react with water. The white salt, the white solid powder, when it's made to react with water, NaOH is a strong base. I'll just write SB, my initials also. And this is orthoboric acid. It's a weak acid. So overall, whichever is stronger, its characteristics will predominate. So it's a strong base and it's a weak acid. So the overall solution will be alkaline in nature. It's very important to know the structure of borax, the hybridization, the how many BOB linkages, and also its nature when you hydrolyze it and the products too. Fine. Properties. Just heat the white powder. It will turn into a fluffy mass because it loses its water of crystallization. And then when you continue heating it strongly, it turns into a glassy bead. That forms the basis of the borax bead text. And the formula of the glassy bead is NaBO2 plus B2O3. So now, if you want to identify an unknown salt, not all, but certain specific ones, then what will happen is you take that borax powder in a platinum loop, the way you do a flame test. And first you heat it, it will turn into a fluffy mass because it will lose its water of crystallization. Continue heating, it will turn into a glassy bead. Girls, you've seen the beads and the glass transparent beads will just look like that. Now, whatever salt you want to identify the basic radical in it, take it, just take a bit of it on that glassy bead. And when you heat it strongly, some of them will form colored metaborates like you'll get a blue colored metaborate if you get a blue colored bead. I'm sorry. If you get a blue colored bead due to a blue colored metaborate, I'm correct. Then it's copper. If you get a dark blue, cobalt, pink, manganese, green, chromium. So the color of the metal metaborate will help you identify the metallic cation present in the salt: dark blue, purple, pink, blue, and green. So certain metal salts, not all definitely, can be detected by this method because they form certain typical colored metaborates. So this is your borax bead test. So at around 100, it swells up by just losing its water of crystallization, becomes anhydrous. Further, if you heat it very strongly, this is a formula of that borax bead or glassy bead. In that, yes, means though these two components are present, this is the active part in it. Yes, so when B2O3 reacts with the particular metal oxide, it forms the corresponding metaborate. That's what is shown here, and we don't have so much of time. Hence, same thing. It will just show you how, in case you want. Chalo, a minute. The loop, hot loop, borax powder will turn into a fluffy mass because it will lose its water of crystallization. Then, and if you continue heating, will turn into a transparent bead. Suppose you want to detect some basic radical, mix it with that desired salt, and when you heat it, the transparent glassy bead will turn either blue or purple, pink, or green, as I mentioned earlier. Yes, that's what it is all about. Now, orthoboric acid or boric acid. Students, I would like to know the N factor of this particular acid. You're aware everything is over, physical, everything is over. Help me with the N factor of this acid. When you
1.
hydrolyze, absolutely correct. So what kind of acid is it? Does it have the ability to lose its H plus or some other types?
Weak monobasic acid.
Absolutely, it is a weak. Why weak? Because its extent or degree of dissociation must be less, right? No, Faizan, it's not 3. It's not 3. What happens is B. Can I write it as this? H3BO3, yes, I can.
Yes, ma'am.
So what happens is when I write it as this or this, can I say boron doesn't have a complete octet? It's short of 2 electrons.
Yes, ma'am.
Very good. When it's short of 2 electrons, it needs 2 electrons. Like so, which kind of electron acids are electron pair acceptors?
Lewis.
Lewis acid. Hence, it's a Lewis acid. And how many electron pair? Very good. When I'm seeing the chats also simultaneously. So what kind of acid is it? Lewis acid. Correct. So how many electron pair does it need to satisfy its octet? So since it needs only one,
1.
exactly, electron pair to complete its octet, its n factor is
1.
1 in that way. It's not a H plus giver. It's an electron pair taker, acceptor, better. Yes. And weak. Why it's weak? Weak or strong by looking at its face or structure? No, we cannot decide. That has to be experimentally decided from its Ka values, from its degree of dissociation. Fine. The equilibrium and all those experimental finding. It is what was found out to be a weak Lewis acid, and its nature is like monobasic as explained now in factor 1. So these are the methods of preparation of boric acid. You can hydrolyze BCl3. You can treat borax powder with concentrated H2SO4 to obtain H3BO3 along with Na2SO4. You can also use one more. You can hydrolyze borax powder and you get H3BO3 and NaOH. So H3BO3 doesn't look the way I have drawn. Yeah, it looks. But what happens? No, it is not alone. It has many other friends with whom it can hydrogen bond like this. So B, OH, OH, OH. What can you expect the hybridization of this boron to be? Absolutely correct. N- No, I'm saying the chats. Yes, it's sp2 hybridized and linked or bonded to the other H3BO3 molecules via hydrogen
Hydrogen
bonding.
bond.
Very good. Hydrogen bonding. Planar, sp2 hybridized, linked with others by means of hydrogen bonding. Yes. It can say water. Donate me a pair of electron. Yes, water can act as a Lewis base and can bond, its OH minus can bond with BOH whole thrice. H plus will be there. So it can act as an electron pair acceptor. It basically reacted with OH minus of water combined with it like this. So you have B, OH, OH, OH. So water is there, but water will attack later on. H plus will be lost and the hybridization of boron changes from the students water attacks
Sp2
and it
to
becomes
Sp3.
OH2 plus. Very good. So I hope you understood that. It's basically
Yes,
OH minus
ma'am.
retained, H plus kicked out, and hybridization. Very good, very good. Sp2 to Sp3. One correction, H3BO3. You heat it, converts into this one is metaboric acid. Further heated, finally you will get B2O3, the anhydride. So H3BO3, heat it above 370 Kelvin, Metaboric acid further heated strongly, B2O3. It also in between forms tetraboric acid. Also, don't get confused with more things. Already a lot of things are there. So meta, and finally you heat it strongly, and finally you get B2O3. That will more than do. Okay, the hybridization change here to here. Is it an acid-base reaction in a way? Yes, I can take. Can I try this with this? An acid, a base, and I get a salt of this kind, Na plus B OH whole 4 minus. Correct? No? Acid and a base forms a salt where boron is happy to accommodate one more OH minus, so that boron's octet is now complete. Boron changes from sp to sp3. Fine?
Yes, ma'am.
Okay. Borate radical. Add some alcohol to boric acid. Ethyl borate, which is formed, is volatile in nature. And just like the flame test, this particular volatile substance burns with a green edged flame. So when you add some ethanol to boric acid and heat, you get a volatile ethyl borate which burns with a green edged flame. A test for borate radical. Diborane. Diborane. After its preparation, I'll go back to some of the slides which are there to show its special behavior. First, tell me, diborane is rich or deficient? Or okay, neither rich,
Deficient.
deficient. What's the hybridization of boron and diborane? No, no, no. No, Faizan. No.
sp2
Deficient is
hybridized.
correct. It is not sp2. It isn't sp2. And for that, we go back to certain things where I here. I'll draw it and show. That will be better. Followed by B2H6. No, right now nothing is there in the slide. I don't want to show you beforehand. I want to explain you first. So if you talk about B2H6, the first thing which will, I'm sorry, thing is got inside. The first thing which will come to your mind is boron, boron. Two borons. Or how many valence electrons? Yes, Faizan, correct. How many valence electrons are there for boron? Three valence electrons are there. So one is busy with hydrogen normal bond. Other is also very busy with hydrogen normal bond. Same case here. So out of three valence electrons, two valence electrons are very busy with hydrogen, forming normal bonds. One, two, three, four. Two more hydrogens are there, right? I should use a different color here. So students, there are two more hydrogens, and boron has now one more valence electron which is not bonded. Boron says I have one more electron valence which is not bonded. Hydrogen says I have also only one electron. This is a normal bond, no problem. Boron gives one, hydrogen gives one. These two will be counted for both normal covalent bond. You know very well now. Bonding is also over. A normal bond, a normal bond, a normal bond. Now I am left with 1, 2, 3. Forget the lower part also. I am left with BHB. And I can see only one valence electron from the boron side. Hydrogen, one valence electron. Boron has one valence electron, but it has preserved it for the lower side weight. So basically, 1, 2, 3, 4. Four electrons. I hope you can properly see. 1, 2, 3, 4. Four electrons and 1, 2, 3. 1, 2, 1, 2, 3, 4. With four electrons, four bonds can be formed. There are just four electrons. How many electrons are required for normal bonds? 1, 2, 3, 4, 5, 6, 7, 8. Double. I need 8 electrons for 4 normal bonds. And I have just for 4 electrons are there. 4 electrons are there uh, instead of 8. So 4 electrons are there instead of 8 electrons. So how do we manage? Happens no, some in the classroom some 3 or 4 people have brought the geometry box. Some high school exam is going on. What they will do? Manage.
Sharing.
Sharing, yes, in a typical way. So now what kind of sharing am I going to show? Let me show it to you. We 3 people will somehow, so 4 electrons now, half will divide. So we 3 people are going to manage with 2 electrons. That's the other way of calling it, 3 centered, 3 people managing with 2 electron. Here also, and where? Here also. We 3 people. So one boron has to give it to the lower side, the other boron to the higher side. Hydrogen 1 electron, hydrogen 1 electron. So 3 people we have to manage with 2 electrons. That's a specialty. And one more special thing is these 4 hydrogens are present on the same plane as that of boron. So they are called as green is, nah, I'm extremely sorry. The color would not be visible properly. Yes, terminal hydrogens. Whereas if I just circle them, and this hydrogen is, by the way, present above the plane, and this one, the lower one, below the plane, and this 4 on the plane. These one on the plane, above the plane, below the plane. So these are known as
Bridge
bridging
hydrogen.
hydrogens. Bridging hydrogens, correct. The same story is written here. Yes. And by the way, yes. Don't know whether it looked or not. This way. And again this way. Looks like banana, and I don't draw it that good, by the way. Yes. It is known as like this.
Banana bond.
Banana bond. Yeah. Correct. So, okay. The way I have explained. Normal bond, normal bond. I know if I do it, it would be easier for you than this. A normal bond, normal bond, normal bond, normal bond. And now we are left with only 4 electrons instead of 8. So these 3 people will manage, 3 people managing with 2 electrons. Up also, below also. These 4 hydrogens, the red ones, terminal ones, are not present on the same plane as that of boron. While the bridging hydrogens, one is present above the plane, the other is below the plane, and it looks like a banana. As you now they have made it very clear, banana bond. Yes. So hybridization, 1, 2. I know these two are not proper bonds, but bonds. So the hybridization of boron should be, see how nicely they have shown. 1, 2, 3, 4. Same plane, one up, one down. Very good. sp3. sp3. 4 terminal hydrogens and 2 bridging hydrogens. 4 normal bonds. Normal bonds are means 2 centered, 2 electron bonds are normal bonds. 2 people sharing 2 electrons is normal. How many such bonds are there? 4. 2 centered, 2 electrons, normal bonds. Remaining 2, 3 centered, 2 electron bonds. Shortage, no? Instead of 2 people sharing 2 things, 3 people are sharing 2 things. On the plane, on the plane, on the plane, on the plane, up, down. Means above the plane, below the plane. If this is up, down, vice versa. Anyone you take. Electron deficient, definitely. Three people managing with two electrons means really short of electrons. So hence it's an electron deficient species. Yeah, it was found out that this bond angle is more than this bond angle. Bond length X more than Y. So many things I would not definitely pressurize you. Know the most important things, basic ones, and then a few things here and there. It's okay. Bond angles and bond length. Okay. Get an idea of the hybridization, the geometry, the bridging, the terminal ones. So that would be more than enough for me. Yes. These values and all, you do it in your with your own will, it's okay. Otherwise, it's too much for you. Because it's just the beginning. There are the other chapters in P block too. Fine. Anyways, coming back to the point, students, the proper bonds are the terminal bonds. So in case substitution has to take place, only 4 out of the 6 hydrogens can participate in normal substitution reactions. The remaining 2, the bridging ones, should be not disturbed. They are already troubled and they are not already in the normal bonds. So in case substitution needs to take place, we should not disturb those poor creatures. Yes. Please answer this. Anyone, quickly. Yes. Yes. Option?
4 and 2. Third option.
Done. Done. Now I gave a hint. Cannot. You cannot disturb the dash hydrogens. Only the dash. Exactly. Students, you can maximum replace 4 hydrogens with methyl groups. The remaining 2 are bridging hydrogens. You cannot disturb them. Everyone got it? That's it. You cannot
Yes,
replace
ma'am.
the hydrogens with 5 methyl. Only 4 can be replaceable. Okay, very good. You all are very, very good, giving so fast answers. Yes. Very quickly, if you want, though we have already completed. Uh, you must have completed. I mean, maybe in a different batch. Yes. This students, if it's beryllium, just see because it's similar. I'll just take 5 minutes and sum up all the remaining things. So purpose is only diborane here because boron is boron family. This is already done. This family members are done. S block. S block done, right? As
Yes,
informed to
ma'am.
me. S done. So just see. Now what happens is this. Same thing. If B2 if B2H4 has to be formed, B2H4, open the bracket, it's B2H4. Then similar thing they have to do. There are only two valence electrons. Same logic. So it's here in the slides. One, two. One, two. So this is hydrogen's electron. Again, three people, BHB, BE. I'm sorry, BE. BEHBE. Again, three people are managing with two electrons. Same logic. Same logic. Diborane is important. But again, the same logic extended here. Same logic. BEHB. Three people managing with two electrons. Again, three center, two electron bond. Hybridization of this beryllium is 1, 2, 3 means sp2. Plain. sp2 means planar. Obviously electron deficient because again, three people are managing with two electrons. A similar logic. We needn't spend much time. That's true in the vapor phase. BeH2 forms a dimer in the vapor state. In the solid state, okay, that much is not required, but in case, just give me a minute. Thank you so much. Yes, in a similar manner, what will you expect? Rich or deficient? Just follow the same logic. What do you think? Rich or deficient? Deficient, right? Because again, three people are managing with two electrons. Yes, very. So many people are answering. So nice. So three people are managing with two electrons. The hybridization is sp3 because one, two, three, four. Students, do you all know that it's only the hybrid orbitals always form sigma bonds and unhybridized orbitals form pi bond? That is known to you, right? Okay, fine, fine. Now, so the hybridization changes so much you don't need, but I just wanted to tell you that all these are deficient people. My focus definitely on diborane, boron family I'm discussing. Yes, I will now tell you something about this. What happens is generally BF3, generally BF3, where it is, wait, I am searching. Yes, generally what will happen is BF3. hmm, What it will do is does boron have a vacant orbital here? Is boron short of two electrons to complete its octet? Yes.
Yes,
Yes,
ma'am.
back bonding. Yes. So what happens is, and one more important thing about back bonding is the compatibility. Like this is 2p. Only because this pi back bond will be a pi type of bond because sigma is already there. Now the next bond which will be formed by the filled orbital of fluorine and the vacant orbital of boron. Filled 2p orbital of fluorine and vacant 2p orbital of boron. Would you people agree that this vacant 2p filled 2p 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 small and compatible also, both are 2p 2p and small? For pi orbital formation they have to come closer. Sideways overlap is as such very weak, so if the orbitals are at least small and compatible they can form a proper pi bond. And is it a type of pi coordinate bond? Coordinate because boron is only taking and fluorine is only giving. So it's a coordinate where fluorine is donating to boron. Boron is only accepting. So coordinate bond. Pi type because once bond is already there, which is sigma type, the other bond has to be formed by sideways overlap. So pi type. Clear. Coordinate because fluorine is the donor, boron is the acceptor. Pi because one bond is already there, the next bond has to be a formed by sideways overlap. So pi bond. And intramolecular definitely, and definitely one is completely filled, the other is completely vacant. And if it's 2p 2p, okay, at least they can come closer and they can form a strong pi bond, a strong effective pi bond. Fine. One is 2p, the other is 3p, okay, accepted. Such back bond is also possible, exist. But what happens, no, like in AlCl3, that's what I'll show, why dimerizes and doesn't form a back bond. Chlorine has lone pair to donate, aluminium has vacant orbital to accept, but the problem is the the p which accepts is 3p, the p which donates is 3p, they are both are quite large. So effective back bonding or effective pi bond formation will not occur. So both 3p orbitals means quite large size. Effective back bonding will not take place, and hence I'll go to that slide. AlCl3 will prefer dimerizing. How? I'll show you. So right now, same. For back bonding, there should already be a covalent bond. So the next bond which will be formed will be pi type. Either at least one of the orbitals should be of 2p type. So 2p 2p okay. 2p 3p also okay. 2p 4p also. I don't know how much practically cost possible. Theoretically we can go for, but slowly the extent of back bonding will be decreasing. One of them should at least have a lone pair. They should have someone has something to give, the other should have a vacant orbital to accept. There should always already be a covalent bond. BF3, think BF3, already covalent bond. Fluorine has a lone pair to donate, boron has a vacant orbital to accept. So both should be either 2p 2p or 1 2p other 3p 4p is, as I said, and it becomes slowly difficult if the compatibility decreases. So these are the effective conditions for back bonding. Where are those? Those conditions we'll see. See. Okay. So the other fluorines become angry. Why fluorine only the left hand side one? Left hand with respect to me. Why only you are ready to donate? What will I do? Okay, you can also donate. The other says, okay, you can also donate. So something becomes like a resonance. So the single bond which you see due to back bonding, all the three bond lengths are equal and they have a double bond character. So all the three bond lengths are equal and the bond length lies between a single and a double bond. Okay, both the atoms belong to the second period and 2 pi 2p 2p back bonding is possible. Correct? No? 2p 2p compatible. All the three bond lengths are neither single nor double due to back bonding. The bond length lies between a single and a double bond. Yes. Now, is back bonding possible here? Think. This is correct? Yes or no? Nitrogen says I have a lone pair to give. Does these silicon atoms have vacant orbitals to accept? Think. Which vacant orbital? Yes, very good, very good. Silicon has vacant 3d orbitals to accept. No, where the heat's possible. Silicon. If it's carbon, not possible. If it's carbon, not possible. If it's silicon, yes, silicon can accept it because silicon is a third period element. 3d is available. Okay. Understood? So, can I ask you people a question? So, if I would like to ask you what is the hybridization of the nitrogen? So, back bonding is possible, as you can see. Nitrogen's hybridization, sp3 or sp2? These are the two only options. Very good, sp2. The lone pair is already donated to any one of the vacant orbitals on silicon. It's not available. So, you can see only three bonds, 1 2 3 pi type coordinate bond, pi type bonds, not hybrid orbitals. So yes, the nitrogen due to back bonding instead of sp3 it's sp2. Very good. Shifali, Vedehi, Fezan, everyone good. So many people are answering. So students, what happens is what you see as a normal bond. What you see as a normal bond due to back bonding, it's actually the bond or it's not a single bond. Not even a double bond. It's in between a single and a double bond. Bond order increases. Bond strength increases. Bond length decreases. So a lot of things happen due to back bonding. Where is that slide? 1 second. Now I can ask you. In which of the following case back bonding is present? This one to be showed. Fluorines
Yes,
2p
ma'am.
donating to the vacant orbital of 3p. There. Bf4 minus. This is Bf4 minus. Back bonding possible. Does boron have a vacant orbital to accept now?
No, ma'am.
Very good, very good. Just now we saw this
Yes, ma'am, it's possible.
because it's silicon. Yes. NF3. No, because nitrogen has a lone pair to give. Fluorine also has a lone pair to give. Who is the taker? Nitrogen. The answer is nitrogen doesn't have a vacant orbital to accept lone pair. It already has a complete octet. No more space. And you know second period elements cannot expand their octet also. You know this?
Yes. Yes.
AlCl3, 3p, 3p. At least one of the orbitals should be 2p for effective sideways bond formation or pi coordinate bond formation. 3p, 3p, back bonding is not possible. What is possible is this. Aluminium says, oh, I am not having a complete octet. Both 3p, 3p, donor as well as acceptor, not very happy. I mean, can't form back bond because both are very large orbitals. At least one of them should be at least 2p to form some kind of effective strong back bond. So what happens is this is what happens. It says, okay, I can't form an intramolecular back bond. Imagine I have AlCl3, AlCl3. This lone pair is donated to the vacant orbital of chlorine. This lone pair is donated to the vacant orbital of this, aluminium. This chlorine to this aluminium, this chlorine to this aluminium. Al2, Cl6. Dimer formation. Can I call it three-centered? 1, 2, 3, 4. 4 electron bridge bond. 1, 2, 3. Aluminium, chlorine, aluminium. 3 people with chlorine is sharing this 1 electron here. Here both are contributed as a coordinate bond. So 1, 2, 3, and this is aluminium's normal electron. So 3 centered 4 electron bridge bonds are formed. No back bonding possible. Wants to have a complete octet? Yes, it has a complete octet via dimerization. Fine. And can I quickly ask you people a few questions so I can drink some water? Meanwhile, tell me. Tell me. Why does TlI3 doesn't exist? Make it very fast. Yes, due to inert pair effect because Tl plus 1 more stable than Tl plus 3. Very good. Students, which of them doesn't exist at all? I know I've not discussed this. Lead comes in the 14th group, and that's the way I am to make you do a lot of things. I minus hint. Okay, I got the answer. Is a very strong reducing agent. It reduces Pb plus 4 here to Pb plus 2 due to inert pair effect. Pb plus 2 is more stable. So a strong, or can I also say Pb plus 4 is a very strong oxidizing agent
Yes,
because it
ma'am.
get reduced to
Yes.
Pb plus 2 very effectively. So a strong oxidizing agent and a very strong reducing agent cannot exist together. D. Very good answering. Anyone, anything, please let me know. Students, is it due to the same reason that BiCl5 doesn't exist? Okay. But I would like
Yes.
to ask one thing. BiF5 exists or not? In that the same logic, Bi plus 3 being more stable, Bi plus 5 is its plus 5 here also, but it exists. And what's the reason which is provided in most of the places, in all the places? Fluorine is quite small in size, and 5 fluorine atoms, arey wah, d orbital contraction. D orbital will contract here because fluorine is small in size and high in electronegativity. Pezan? Good. Wow. We'll come to these things later. The pre-block journey is there. Today, I would like to more focus on 13 and follow a systematic pattern. What an answering. What a batch. Yes, yes. So, due to inert pair effect, Bi plus 3 is more stable. BiCl5 doesn't exist. If anyone, if we go further here, BiF5 do exist because you have already studied about d orbital contraction in chemical bonding, some must have discussed. And here, yes, that's true here because of the small size and high electronegativity of fluorine atom here. Good, good, good. Again, plus due to inert pair effect, plus 2 more stable than. Similar things what to ask, you'll be saying are wasting our time. Yeah. So BiF5 exists, BiCl5 and others do not.
Fourth option.
Absolutely. Okay, back bonding. Yes. PP, P pi, P pi type, both are 2p, 2p. The other one is P pi, D pi type, where nitrogen's P is donating to the vacant 3D of. So filled 2p of nitrogen donating to vacant 3D of silicon. And definitely, once you see back bonding, bond order will increase, bond length will decrease, bond strength will increase. Okay, that's also there. Definitely, if you talk about Lewis basis, basic strength, you saw that the lone pair was not available due to back bonding. So the basic strength was decreasing. By the way, if you compare the acidic strength of BF3, Lewis acid strength, it's a Lewis acid boron is short of 2 electrons to complete its octet. So if I compare BF3 versus BCl3, chalo, that would be good enough. Lewis acid strength. Can you help me out? Where is more back bonding? And if back bonding is more, Lewis acid strength will be more or less. Good. So BF3 more back bonding. 2p 2p more compatible. So with more back bonding, what am I doing? If I see more back bonding in BF3, so if the back bonding is more, it's no longer that efficient, right? So Lewis acid strength, it's less deficient now, will be less. So the extent of back bonding is more, Lewis acid strength is less. So this is a Lewis acid strength order. BF3, more back bonding, less deficient, weak Lewis acid than BCl3. Yes, more back bonding, less, 1 second, less Lewis acid, and very, very good. So in that sense, bond order will increase, strength will increase, length will decrease, Lewis acid character will change. If back bonding is there, Lewis acid strength, Lewis basic strength will be less. Back bonding not there, those Lewis acid and basic strength will be more. Hybridization. In the case of BF3, boron's hybridization did not change. Am I correct? Boron's hybridization was sp2 and will be also sp2 after back bonding, right? Yes. But what about that N? So BF3 after back bonding also sp2 only. N SiH3 whole thrice. The lone pair is not available given to the empty 3D orbital of silicon. So this back bonding hybridization changes because if I replace silicon with carbon, the nitrogen's hybridization, now the lone pair is available. sp3. Yes, very good. So hybridization may or may not change. That's the reason. Geometry of the molecule may or may not change. Yes, because here it's planar, while here it is pyramidal, right? Trigonal, pyramidal. So geometry may or may not change, hybridization may not change, but definitely Lewis acid and basic strength will decrease due to, depends upon cases, here Lewis base, here Lewis acid, due to back bonding. So these are all effects of back bonding. Tell. Chalo, let me revamp this question. Okay, got the answer without revamping. This is the only case where back bonding is seen, right?
Yes, ma'am.
Very good. Correct? It's already given. And so minimum, so maximum back bonding, minimum back
Back.
bonding, and hence maximum Lewis.
Lewis acid strength.
Absolutely. Good. Good preparation. Same. If the central atom is okay, we'll see sequentially. If a lone pair of on donor participates in back bonding, okay, then it's okay. Right here. I'll explain quickly. The lone pair here participates in back bonding. So the lone pair, wherever it is present, will not be considered as a hybrid orbital. Correct? You are participating in back bonding. You are not available on nitrogen, so you will not be counted as a hybrid orbital. Okay, fine. If the central atom is acceptor, boron, the central atom acceptor, suppose in BF3, boron's hybridization doesn't change. So the central atom is the acceptor, say BF3, its hybridization is not changing. Okay. The lone pair is involved in back donation. Then it will not be counted as a hybrid orbital. Yes, hence it's sp2, not counted in hybrid orbital because it's not present there. It's involved in back bonding. Fine. Okay. Students, compare the, call this 1 and 2. Compare the Lewis base strength, in which case it's more. Very good, first one. Back bonding, in which case I'll put a tick. I hope nothing is given there. Oh. Back bonding there? No. Yes. sp3, this is not there. It's involved in back bonding, not available. So it's only sp2. Planar, pyramidal. Bond angle, if it's planar, it's around 120. Pyramidal, it should be
Less
slightly less than
than
109.5.
1.
Non planarity around nitrogen, non-planar. Around nitrogen means if I consider the lone pair, then non-planar. If I consider the lone pair, then non-planar. If I don't consider the lone pair, then I can pass a plane through this. Non-planar including the LP. Chalo, planar. Lewis base strength, more, less, none, not applicable. Lone pair is very busy in back bonding. Here it's available. B3N3H6. Borazine, borazole. This is inorganic benzene fezan. Yes. Where both nitrogen as well as boron is sp2 hybridized. sp2 planar. Planarity is an important condition for resistance. So B3N3H6. When it's there in some of the slides, when B2H6 diborane and ammonia react in the 1:2 ratio, boron, why am I calling it boron? Diborane and ammonia react in the 1:2 ratio. It is formed. Seeing this pi electron cloud, alternate double bond, six-membered ring, not carbon, but very similar to benzene. It's called as inorganic benzene. Yes, planar. Both nitrogen as well as boron are sp2 hybridized. It's okay. Yeah. Can you tell me? I should have actually asked which is more reactive, inorganic benzene or normal benzene?
the answer is already given. It's inorganic benzene which is more reactive. Why? Inorganic benzene, did you see? Polarity. Can I expect that nitrogen is giving, so it has a plus, and it's a coordinate bond, right? Minus plus. Nitrogen, the one who gives is gone, loss. The other one which takes is gaining. So because of this charges, a polar, yes, polar bonds, very good. Polar bonds. Due to polar bonds, inorganic benzene is more reactive than benzene. And yes, you've already learned about diborane. And yes, I was talking about this Al2Cl6 types, in which there are three centered 4 electron bonds. Yes, this one we have seen. Okay. Yes, here. Diborane's preparation, lithium aluminium hydride plus BF3. Sodium borohydride plus iodine. Can you help me recollect? Because you've studied organic and that also completely. What are these two? And what are these two? Quickly. Reducing.
Strong reducing agents.
Very strong reducing agent. Out of the two, which is much more stronger than the other one?
Lithium
Exactly. And
aluminum hydride.
yes, because the bond is much more polar, so it has more ionic character. Lithium aluminium hydride. Which out of the two can reduce esters? Both esters.
Lithium aluminum hydride.
Very good. Very good. Okay, one more methods. Very good. This is the way you should correlate and study. Structure we have seen. Okay. Sorry for this. Yes. Yes. So students, B2H6 can be cleaved or broken in two ways. I'll show you how unsymmetrical, symmetrical. I'll explain you wait through these examples. Yes. Now imagine B2H6 is deficient, right? And CO has, see the structure of CO. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So CO basically has a lone pair on oxygen as well as on carbon. So it's a Lewis base. So if I consider CO like this, and if I imagine B2H6 as 2 units of BH3, so what do I expect? Definitely I expect carbon to be donating a lone pair, carbon to be donating a lone pair to the vacant orbital of boron. Carbon, you have a lone pair, oxygen you have. Why does carbon donating? Carbon is less electronegative, so it will have greater, very good, in the chats. It is having greater willingness to donate, so it will donate to the vacant orbital of boron. And I have split it up as BH3 and BH3. So I will take two, I'll just write a 2 and my job will be easy. 2 units of BH3 with 2 units of CO. I'll take 2 moles of CO and it will form a coordinate bond of this type. And here also same logic. So this symmetrical cleavage of B2H6 produces 2 units of BH3 and each unit is a Lewis acid and can react with CO the way I have mentioned. Yes. Unsymmetrical cleavage. Remember these three reactions like B2H6 plus excess of ammonia at low temperature. It forms an addition product B2H6 dot 2NH3 which can be split into this because you're splitting it in an unsymmetrical way as BH2 plus and BH4 minus. When you're splitting it in this way, the plus part ammonia gets attracted. Ammonia has a lone pair. So the plus part ammonia gets clinged to it and the minus part remains like that. So either you remember it this way or this would be good enough. When B2H6 and ammonia react, an excess of ammonia react but at low temperature, these two conditions. First thing to remember, there's an addition product which is formed, and this reveals the unsymmetrical cleavage of it. It's okay. Anyone is good enough. Now, when the same thing happens with excess of ammonia, but not low temperature B2H6.2H2O. I'm sorry, B2H6.2NH3. High temperature. Excess of ammonia at high temperature, inorganic graphite is formed. Graphite has a layer structure. The different layers in graphite are held by van der Waals forces. Something similar, but definitely you here it's a polar molecule. So something similar will be called as boron nitride, borazone. Zol and zine is inorganic benzene. Zone, on, or inorganic graphite. This kind of structure. Excess ammonia, high temperature. Excess ammonia, low temperature, B2H6 dot 2NH3. And if you have not excess ammonia, diborane is to ammonia into 1 is to 2 ratio at high temperature. Inorganic benzene is formed. These two, very important. So both are high temperature. I take two the same thing, diborane and ammonia, both at high temperature. If it's excess of ammonia, inorganic graphite or boron nitride. If it's limited amount of ammonia, that's in the 1 is to 2 ratio, borazone or borazine is to ammonia is 1 is to 2 ratio at a high temperature. At a high temperature. Then what we get is, you people will try once, inorganic benzene. Let the slide be there. So boron, why do I call it boron? I'm sorry. Diborane is to ammonia in the 1 is to 2 ratio high temperature. What do we get? Diborane is to ammonia in the 1 is to 2 ratio at high temperature.
Borazine.
Inorganic.
Inorganic benzene, borazine, borazole, done. Diborane is to an ammonia. Diborane and ammonia, high temperature, excess of ammonia.
Inorganic graphite.
Inorganic graph.
Excellent. Or boron nitride. Diborane and ammonia, excess of ammonia, low temperature.
E2X dot 2H.
B2H6.2NH3. Excellent. Very good preparation. Chalo, very quickly answer this. Inorganic graphite, not benzene. Option? Without any doubt. Yes. Alum. Students, they are double salt. And let me talk about potash alum. This M is monovalent. Its valency is 1. This M dash, its valency is 3. So when you have K2SO4.Al2SO4 whole twice dot 24H2O, double salt. Double salt means two simple salts are generally equal. Equimolar solutions of two simple salts are taken. They are heated together, and on cooling, when they crystallize and form a salt, where the individual ions retain their identity. Double salt. If they lose their identity and form something new, complex salt. Coordination we will see. Fine. So this is a monovalent radical sulfate, trivalent radical sulfate dot 24H2O. That's alum. In which you can remember other things. Yeah, Faizan, correct. Potash alum is something which you need to know or remember. Try to remember these uses as much as possible. Boric acid is used in that, like eye wash antiseptic. Borax is used in the production of heat resistant glasses, aluminium and aeroplane pipe, slippery nature. This one you must be knowing. That carom board powder is nothing but boric acid powder. Beat an isotope used to absorb neutrons to control the chain reaction in nuclear chemistry. Boron fiber to prepare bulletproof vests. Because of its high melting point, maybe no? Fine. No. Yes. Tell me which element in group 14 shows inert pair effect. Very good.
Lead.
Pb, which is more oxidizing, Pb plus 4 or Pb plus 2?
PB+4.
Very good,
PB
because
plus.
Pb plus, yeah, Pb plus 4 is a very good oxidizing agent. Why? Because an oxidizing agent should oxidize others and itself get reduced. So Pb plus 4 will be very happy to reduce to more stable
PB plus.
Pb plus 2. The salts of lead are acidic, basic, amphoteric in nature.
Basic.
Something else? Anyways, I think so. I'm planning to start group 14 tomorrow only. 3 4 minutes are left. I can ask you certain questions. Yes. So the oxide of lead is acidic, basic, or amphoteric in nature. Tell me, tell me, tell me. I didn't hear. Amphoteric. Oh, sorry, sorry. I didn't hear and I didn't see the slides. Very good. So group 14 we can discuss in the next class. Meanwhile, I can tell you something very briefly about the hydrolysis. Students, hydrolysis you have already learned from the, yes, very good. From the chats I'm answering. From the ionic equilibrium viewpoint, tell me which particular salts do not undergo hydrolysis. Yes, salts of strong acid and strong base. Very good. Now, students, here in hydrolysis, since you have also already learned organic chemistry, so if I have something like BCl3, can you understand that OH is a stronger nucleophile and Cl minus is a good leaving group? That language you'll understand? Okay, fine. As a result of this, what happens is if I take 3 water molecules, the 3 Cl groups get replaced by 3 OH. So this is the logic behind hydrolysis. But yes, boron, because what happens is this. Um, BCl3 is there and say one water molecule Lewis base is attacking. Temporarily, no, what will happen is Cl 3 Cls will be intact and this temporarily gets attached and a transition state. I know you know the transition state is very unstable, right? This kind of stuff will be formed. So would you like to accept that because such transition states are formed in the mechanism, the central atom should have vacant or orbital? Because I know Cl going and OH coming, but there will be a temporary state where OH and Cl both will get attached to remain attached to it. Agreed?
Yes, ma'am.
Fine. So for
Yes, ma'am.
hydrolysis, it's basically the other nucleophiles like mainly halides and all we are discussing. Halides being replaced by OH groups. OH is a stronger nucleophile, so weaker base goes out and strong base comes in. And the central atom should have a vacant orbital to accept that. Yes, this one I discussed. So students, temporarily, the boron's hybridization will be sp3. For so temporarily, it has to not leave Cl and accommodate OH2. Okay, 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 Faizan. Yes, yes. So in that situation, for that reason, the central atom should have a vacant orbital to accept this electron. One more thing I would like to ask you. I have CCl4. Can it undergo hydrolysis? Same thing they are showing here. I have CCl4. Can it undergo hydrolysis? So if the hybridization is suppose sp3 for the reactant, temporarily in the transition state, it will undergo a temporary change of hybridization to sp3. That's what they mean. What I was asking is, I know one within a minute I'll end up. I know it's time. So what I was asking is, I remember. CCl4. Can CCl4 undergo hydrolysis? No. Carbon, yes. Carbon already has a complete octet and it's a second period element. It can't expand its octet. So in the it doesn't have a way out to show to justify the transition state. It doesn't have a vacant d orbital to accommodate those extra electrons from water in the transition state. Yes. One more very important thing is, you know, from the Fajan's rule, the how to decide the covalent characters. The cation should be small in size, highly polarizing, and the anion should be large in size, can get polarized easily, and high charge on the cation and anion. So the covalent character is more, the extent of hydrolysis is more, because the entire hydrolysis stuff is done to covalent compound by breaking covalent bonds. So the degree or extent of the degree or extent of hydrolysis is directly proportional to covalent character, and the extent of covalent character you can decide it on the basis of Fajan's rule. Fine. So that's the reason CCl4 can undergo hydrolysis. I'm sorry, SiCl4 can undergo hydrolysis. Yeah, I'll end up now. CCl4 cannot undergo hydrolysis because C or carbon does not have a vacant orbital in it. Fine. See, aluminium, yes, you have a vacant orbital, so we will not have any problem. See how hydrolysis of nitrides liberates ammonia gas. By the way, what is pH3? What is pH3? Phosphine. Phosphine. Yes, yes, yes. Fine. So tomorrow we can discuss about group 14. Students, could you follow what I said? The pace has to be little fast to complete the things, so many things which are left. Any difficulty in understanding? Should I slow down, or should I change my method? Because every class is based on the students. Like, if whatever you want, you can accordingly adapt ourselves. So it is completely a new thing for me with you, not with in general, with you. So pace is fine. In which module do you refer? I hope you're given the material exactly in that material you have p block 13, 14, and all, etc., etc., comes. So in those inorganic p block, you can refer group 13. Yeah, and it would be good if you read 14 and come. Okay. If not anything else, we will end of today's discussion. Thank you everyone for your patience and
Okay.
cooperation as well. Thank you so much. You were very cooperative. Suddenly I came and you were very accommodative. Thank you so much, everyone. Bye. We'll again meet tomorrow. Okay? Maybe I can get you some 13 group 13 questions in case we have time. Otherwise, we'll start with the 14th group. Thank you, everyone. Bye.
Thank you,
Thank
ma'am.
you,
Thank you,
ma'am.
Thank
ma'am.
you all. Bye.
Bye.